My name is Anton Chunov. I'm from Zilliqa Research and I'm on the Scilla team. So I'm one of the Scilla developers. Let me quickly walk you through the plan to the top. First of all, we will be talking about the so-called safety idioms. And because your contract might be managing lots of money, so you definitely want your contract to be safe. And to achieve that, we have several features. One of them is a language feature called contract constraints. Then I will be talking about checking preconditions of transitions. Then we will be looking at a particular instance of that precondition. That's the deadline idiom. And then we will be talking about how to transfer money between your contracts. So the thing is, on Zilliqa, you can write several interacting contracts in Scilla. And so you might want to actually send some messages, some funds between those contracts. And so you should be sending money deltas and absolute values. And I will be talking about that in a moment. Next, we will be covering some performance tips and tricks. I will remind you how to use maps in Scilla and what kind of different maps we have. And then we will be looking at this case study for how to get field map size. And at the last part of my talk, I will be talking about formal verification of Scilla contracts. So this is my area of expertise. I'm developing a formal verification framework. So I will be giving you a sneak peek of that. So that's still work in progress. It's not been officially released, but we already have some promising results, which I'm eager to share with you. We will be looking at the so-called temporal properties. So properties related to time of one of the important contracts called crowdfunding contract, which is called like a hello world of blockchain contracts. And we will be looking at the tools through which we can do formal verification. So let's start with some safety properties and safety idioms. So the first one is called contract constraints. Let's say you have a multi-signature wallet contract, and I'll briefly explain what it means. So sometimes you want to collectively own some funds. So you might want to create this kind of multi-signature wallet, which will have owners list. So there can be like a bunch of people who collectively own some money, and they decide when to whom transfer those. And then you have some kind of limit called required signatures. So this is the number of required signatures. Maybe you want like 6 or 7 signatures if there are like 10 people collectively owning some money. But that means when you deploy this contract, so right now these are immutable contract parameters. These are not defined as of now. They will be defined when you deploy these contracts. So you'll have to specify concrete values. And it's kind of easy to screw up and put, for example, like an empty list here, or maybe if you have 10 owners, then you can require 11 signatures, which means you probably just freeze your funds forever. So to circumvent this, you can put a CIL expression over here. So we have this special syntax between with and double arrow. You put a CIL expression, which is basically a Boolean, and you say something like, okay, number of required signatures is okay, which means it's within certain limits. So for example, you definitely want the required number of required signatures to be greater than 0. And you also want the same thing to be less than or equal to the length of the owner list. So that's the first one. And I'm skipping the exact expression because I think you got it already. And also it wouldn't fit into the slide. And then you also want to check that in the owners list, there are no duplicate owners. So there are no like copy paste mistakes or whatever. And then you basically check that these two conditions are true simultaneously. That's it. That's simple as that. That's just basically a very simple expression that the Zilliqa blockchain will check when you deploy these contracts with some particular instances of the list of owners. And also, let me quickly remind you that this list of byte string 20 means basically a list of addresses. So byte string 20 is the type of Zilliqa blockchain addresses. And this unsigned integer of 32 bits width, so that's also common in certain languages. Next, let's look at the transition preconditions. So let's say you have fungible token contract, so which means you basically want to implement your own currency on top of the Zilliqa blockchain. So you don't want to use these native ZILs. You use your own currency. And to actually create your own currency, you need to mint it. You need to create new coins. So you might want to add this transition called mint to your contract. So that's just part of the contract, which allows you to give to this recipient, that's their address, right? This amount of your tokens, of your fungible tokens. But you probably already get it that this mint is kind of dangerous, right? Like not everyone can call it on the blockchain. So you want to check that only the owner of the contract can mint new coins. So to do that, we advise to use this idiom called, for example, isOwner. So this is basically so-called precondition, right? Something that must be true before you get to execute the rest of your transition, because otherwise it won't make any sense. Here's a procedure that does some authorized mint, but it works under the assumption that only the owner can call it. So here you can see that we can use procedures like private transitions. So isOwner takes this address, which will be, of course, a sender, and checks that the sender and the contract owner are the same entity. So this built-in EQ, it's equality check. And so you match over this result if it's owner or not. So if it's not owner, you throw an exception, and the ZIL interpreter just basically aborts the execution. That's it. So this part won't be executed. And if it's true, if it's the owner, then you just do nothing, because you can let the control flow to the next stage. So that's a very simple thing. And in particular, we have this particular instance of precondition idiom. We can check deadlines for transitions. So sometimes you need to add the so-called deadline parameter to your contract transition, because there is this thing called the transaction withholding attack. So the miners can actually try to postpone executing your transitions until the moment that is when they can take benefit of that. And so this is important for contracts operating with highly fluctuation prices, like some kind of token exchanges. And so what you do is you add, for example, this transition called buy until. So you can buy something until this deadline. And bnum is the block number. So it's basically like how people measure time on blockchain. And we use the same idiom, the precondition idiom. So if the deadline has not passed, then we do something. And what exactly, it depends on your business logic. So I'm not covering it here. So how would this procedure deadline has not passed would look like? Here it is. We have a special blockchain variable called block number in all caps, like screaming at you. And this is this peculiar syntax we use to read it. So there is a number of different arrows in Scilla. Sorry for that, but that's syntax. You have to pick something. So I can read the current block number. I call it current time here. And then I check if the deadline has expired or not using this built-in, which is called block less than. So if the deadline is less than current time, then it means that current time is greater than deadline. So if it expired, I just throw an exception, which means I won't be able to go over here, right, and do something malicious here. And if it's false, I also do nothing. And this is just the syntax for Scilla commands. So in principle, you can scratch that and just leave empty space here. Moving on. So let's say you have several interacting contracts and you want to pass funds between them. Sometimes people pass absolute values. So they compute, so they have some kind of accounts map or accounts associative array. They compute the absolute values of the amount of funds a particular account holds, and they pass that. So that's not very safe, because when you do that, you basically override account information with fresh value instead of making incremental change. And I'll be explaining in a bit how it can be bad for a contract. So let's see how you can transfer funds the wrong way. So just to be a bit more concrete, let me use some Scilla syntax for that. So this is a Scilla message, right? So this MCG will hold some information. So this update means that I'm going to call the update transition, and that's the address I'm going to send it to, right? I just skipped a bunch of fields, message fields here. So I want to update account with this address with this new funds value. So that's the sender part. That's one contract. And let's say you have another contract, which is your recipient. So it will have the matching transition here and here. You see it's update. It will have these two fields, these two parameters, right? To and funds, just like here. And it will probably have some precondition, like some safety logic here, and maybe also some logic over here. But what's important here is that we just update the accounts map at this address with the new value of funds. And that's dangerous because it may lead to race conditions and also, for example, double spends, because there may be several transition calls simultaneously, and you don't want them to kind of compete for this particular map cell. So Scilla is designed in a way so that these transitions are themselves like critical sections, right? So there is mutual exclusion here. You don't have to worry about someone, interjecting somewhere here. So the DAO attack is not possible here, but there may be several pending transitions which may basically override the same value. So how do you do it instead? So it's basically like the same thing. You just have this message, but you treat the fields a bit differently, right? So instead of new amount, you pass so-called delta, right? Basically a change. So for example, here you would call this update transition, and you would add some amount of funds. It's like when you transfer some funds on the blockchain without any contracts, right? You just transfer money, and the blockchain engine basically takes care of everything else, right? They update your balance with a new value. So how do you do that? You just read the accounts cell into, give it a name called old funds, and then you add this delta to old funds, and then you overwrite only after that. So you can immediately probably see that when you do several updates in parallel, they will be just adding more stuff to the same account. They won't be overwriting. So this is basically saying, okay, old funds is a new name, so it's not a variable. You cannot change it. It's immutable. So here and here, you cannot change it. You just basically assign or give new names to these particular expressions. But this part is, yes, this is assignment. So here the field map accounts would be changed. And so this particular idiom, it avoids race conditions. Okay, and so we are talking about maps. It's one of the most important data structures in Scilla. For example, you can use maps to represent user accounts, something like this, right? You have a field map accounts. You give it a type, you say this is a map, or in some languages it's called associative array or key value store. And that's a type from addresses, byte string 20 is a blockchain address, to the amount of funds this particular account holds. And you have to initiate every field variable or map. And here it says that's an empty map of byte string 20 to uint 128. And in Scilla, you have to explicitly specify all these types by hand because it's an intermediate level language. So it takes a bit longer to actually do stuff in it, but we are working on making it better for the end user, for the programmer. Okay, so we have two types of maps. One type is called field maps, which are mutable and they're very efficient. They are currently implemented as hash tables. And also we have immutable functional maps. They provide a lot of flexibility, but they may be less efficient because of some copying operations, but also you can use them in your libraries. So in the pure part of the language. For example, we sometimes see people using this anti-pattern when they work with field maps. So what they do, let's say we have still our field accounts, just like on the previous slide, and you have this transition called update. You could have called it foo. Doesn't matter what the exact name here. So what they want to actually update some particular key of that map. They want to update some particular account. What they do is they use this syntax. And now you can see all three of different syntaxes in Scilla, how to access variable or a map, or how to read from a variable, how to give some expression a new name. So let me explain it again, just in case, because I know that can be confusing. So this syntax, this backward arrow that says, I'm just reading this value and giving this name to a value in a mutable field. So actually, at the level of implementation, you will be accessing the database here. So that's why it can be kind of expensive. So, and what this line does is it takes the accounts field map and it creates a copy of the whole map. And let's say your dApp is handling a million of accounts. That will cost you some gas, right? So you can clearly see this part is clearly an anti-pattern. Now, this syntax says, okay, new X name stands for this expression here. And this expression means that you put a new key into this map, or you change a certain key, like that is already there in that map. The key is called ACK for account. And you update this key with this amount of funds in this map. And then, so this creates a new copy of the whole map. So if you have like a million accounts in your map, this will sometimes create a new map with 1,000,001 keys. Now then, you also update the accounts map with this newly computed map. So in upshot, that's basically like 3 times, will cost you around 3 times more gas proportional to the amount of the accounts in your map. So once more, this is just read a value from a field. That's just basically give a new name to this whole long string. You can think of it as a macro, for example. This is just a constant. And this means update a field variable. So these 2 pieces of syntax are to handle fields, mutable fields. So instead, people are encouraged to use this simple in-place operation on maps. So if you're handling field maps, you use this. This looks like array operation, array update operation in most languages. So it's just, I think it's familiar enough syntax. So please use that if you want to update your accounts. So one more thing, sometimes people want to get the size of their maps, right? Sometimes they want to know how many accounts they have. But if you look in the Scilla docs, you won't find this operation for the field maps, so the maps that you can actually mutate, you can actually change. But they can find this built-in size operation, which lets them get a size of so-called functional maps. So they create a copy once more, just like we saw before. And then now they can get the size of the map, so they can know how many accounts they have. So that's also pretty expensive operation if you expect your DApp to be working with huge maps, if you want a lot of customers, right? So instead, you can use the so-called account size idiom. So you have this field map as before, and you create one more field variable, which you will be keeping the size of accounts in. This is a variable of type unsigned integer 32, and its initial value is 0, which is consistent with this empty map. Empty map has 0 key value associations. And if you want to get the size of this field map, right, you just read this variable, right? So that's the piece of Scilla syntax for reading from a field as before. Okay, but now we have a bit of a problem here, right? We need to make sure that the map and its size, they stay in sync. That's very important. And you have a couple of operations, couple of statements that may or may not modify the map size. For example, this one. This operation either changes this key to be associated with this value, or if this key is not in the map, it adds new key. Right? So it looks like an array, but in fact, it's not, right? Because it lets your maps grow or shrink, in this case, grow or shrink dynamically. Okay, so this might add a new key, so that might grow your account size, or might not actually do that if you already have this account. Or the same thing goes for this. So if there is a key, it deletes, operation, it deletes it. If there is no key like that, then it does nothing. So it's better to systematically use procedures instead, right? Because it's very easy to actually miss something and forget to update the map size. And so I will be showing you just one simple procedure. This procedure is to insert two accounts, right? So it inserts this key, this address type, and associates it with this value. So we check if there is already a key, named key in the accounts map. And if it's already there, we do nothing because we just update it. We don't change the size. We do nothing with respect to computing and updating the account size. And if it's not there, we just basically, we read the account size, we add 1 to it. So we add this constant 1. It's not shown here, but it's defined elsewhere. And we update the account size. And after that, we just reuse the same Scilla built-in for updating field maps. So that's it. So what is formal verification? And that's the topic that excites me the most. Formal verification is a family of techniques that help us to ensure our programs behave according to their specification, ensure that they are correct. So first of all, you need a specification. And moreover, you need a formal specification. So it's not just like something written in English or Chinese or any other informal language, natural language. You want to read it in some kind of logic. And also, we need tools to connect specifications to our implementations. You can write your formal specification as some kind of logical formula, but then you have to somehow combine, like link them together, right? And doing that by hand is very tedious and not very reliable. Okay, so let me show you what we're going to do about that on this simple example. So let's say you have this crowdfunding contract. So that's contract in the style of Kickstarter campaigns, and it has several parameters. It has the owner of the contract, the one who gets the money from the crowd, right? We have the deadline for the campaign. So that means if it's past the deadline and you get all the funds you needed, then you're okay to withdraw the funds from the contract. Go ahead and implement some cool stuff you were crowdfunding for. And also, of course, you have the goal, right? So that's the amount of money you actually want. And I remind you again that BNUM means block number. So that's like blockchain notion of time. And this is unsigned integer of 128 bits. So that's how we count ZILs or tokens with that. And you have like this accounts field map, right? But here it's called backers. And that's again the same map from addresses into the amount of funds each address donated. And so now in this fragment, I'm showing just the public interface to this contract. So we have a donate transition, which basically lets a backer to donate some money to the contract. And essentially what it does, it checks some preconditions here, which I'm not showing here because otherwise it won't fit into the slide. And when someone donates, we need to be sure that we record their donation here, right? So the sender, so the one who makes this transition, calls this transition, we record that they donated this kind of amount. So underscore sender and underscore amount, these are implicit parameters to each transition. Now we have the so-called get funds transition, which lets the owner of the contract to withdraw money. And also we have some preconditions, like it must be past the deadline and the goal must be met. Otherwise, they're not allowed to withdraw money. And so this send instruction, send statement, it sends, I skipped a bunch of message fields from here, but that lets the owner to be the recipient. And then the amount will be all the money in the contract, accumulated in the contract. And also, since a campaign can fail, we must be sure that the backers can claim back their funds, right? So they can be refunded. And so that's like the same thing here, right? Every backer can get their funds back and not everyone else's, right? So what kind of temporal and safety properties can we specify, can we ask to be checked for? So for example, one of the important properties is that eventually contract's balance is always zero. So that means that we accumulate funds in the contract, and then at some point, after the deadline, either the backers gradually withdraw all the money, or the contract owner can withdraw all the funds in one go using the get funds transition. And then after that, nothing can happen. So the contract is dead and that's it. So what we check here is that everybody can withdraw money. Like the contract cannot freeze your funds. And that's an error you can see here in the blockchain, right? Contracts freezing money. So we don't want this to happen. So we specify this as this. Eventually contracts balance _ balance is the amount of money contract, the amount of ZILs contract holds. And luckily for us, we can express this thing in a temporal logic. So this reads like this. This reads as diamond and this reads as box. And so box means always and diamond means eventually, right? At some point in the future. So this formula reads balance is zero. So if I read this part, always balance is zero, which is clearly not true, right? It's not true that our balance is always zero because people can donate, right? So the balance will increase, but this thing is true for the contract. So eventually the contract wouldn't hold any money, so it won't freeze your funds. Next, this property prevents us from forgetting to put the send instructions. So I showed you on one of the previous slides, the send instructions in the claim back and get funds transition. So these allow the backers to get a refund, or they allow the owner to actually get the money and proceed with their project. So that's very important that we don't forget to put any send instructions. And also, this prevents us from failing to record the donations into backers map. So if you don't record the donation for the backer, it won't also work. That might be a bit less intuitive, but still you can check that. And so another temporal property can be formulated as this: the contract always has enough money for refunds, or you can also say that the contract doesn't leak money. And this can be formulated in temporal logic like this. So this part is kind of technical. This is because when the owner gets the funds, they don't bother with cleaning all the backers map, right? Because that could cost a lot of gas. So they just get the money and all the donations are there, still there, but no one can do anything right after that. So, but what's important here is this part. We are saying that, okay, let's say we have all our backers, we get the sum of all the contributions for all the backers, and that sum should be less or equal to the balance, right? So we have always enough money, more than enough, to actually refund everybody. And what makes this property temporal related to time is this box. So this says always, at any point at execution, this is true. And here's the comment I already made. So how do we actually check that? We can use the model checking approach to actually do that. That's basically related to exploration of the whole state space of the contract. So any state your contract lined up, we can check if the properties are violated or not. Also, let me quickly remark that those properties are not complete, so we have even more of them. So you can never know if it's complete or not, but still, if you have enough interesting properties, that gives you high confidence in your contract. And so the specification, the properties I already showed you, they're written in TLA in language called TLA+. TLA+ stands for temporal logic of actions. Plus means plus set theory. This is developed by Leslie Lambert. So he is one of the fathers of the distributed systems research. So there is a tool in the TLA Plus toolbox called TLC model checker. With that, we can explore all the states that we have. But how do we model check Scilla contracts, right? Because Scilla contracts are not written in TLA Plus, they are written in Scilla. So what do we do? And the answer is simple. We have a Scilla to TLA Plus transpiler, or you can call it translator or compiler, which is still work in progress, but we are showing you the preliminary results we're getting. So with that transpiler, you can translate the whole of your contract. So for example, this is just a fragment of the translation of crowdfunding contract that I showed you before. So this language is called TLA Plus, as already mentioned. And it, for example, we translate the match, the Scilla match statement into this case expression because TLA Plus doesn't have pattern matching, but Scilla does. Also, we have to specify precisely which variables are changed and which are not. And here you can see this unchanged on all caps. So that's TLA Plus syntax for the unchanged variables. And I'm not showing you like pretty big expression over here, but here you can see that sometimes the balance and backers are not changed. And they are not changed in case if, for example, it's after the deadline. Right, we're not accepting any more donations. So the backers map and the balance cannot be changed. Okay, so you combine the transpile TLA Plus code with your temporal properties, like I showed you before, right? Like, for example, eventually always balance is 0, right? And you run the TLC model checker on this thing, on this combined thing. So for example, we already have the crowdfunding contract. You can check out Scilla on readthedocs.io. If you check out that contract, then it's already correct. And this shows you here that there is no error. So this part says it's okay, totally okay. So that's a screenshot from TLA Toolbox. But what would happen if, for example, we had missed accept statement in the contract? What had happened if we recorded the donation from some backer, but didn't really use the accept statement, which basically increases your balance? The contract without this accept statement does not do that. So when you run that TLA Plus Toolbox, you get this kind of thing, this one error. And here it says that invariant called no leaking funds is violated. So that means we have recorded that someone made the donation, but we failed to actually accept the donation. And moreover, this tool shows you the error trace. So you can actually trace the steps your contract is taking to actually reach this forbidden state. And this is really helpful. So with this error trace, you can easily debug your own contract. Here are some useful Scilla resources. Please check them out. And let me just provide a quick summary. So here at Zilliqa, we take safety seriously. So we have an overall safer language design. So for example, inside transitions, you have critical sections. You don't have to worry about reentrance bugs. We have safety language features like contract constraints that wouldn't let you deploy an inherently flawed contract. We catalog Scilla safety idioms, like we showed you already. We picked, for example, this deadline idiom from some cool guys we're working with, our customers. And also we provide this formal verification framework to formally verify contracts. Thank you everyone for joining.